Welcome to the second session of magnetism with me, your physics master teacher, Shreyas. And today we are going to see really interesting geometries. We are going to see the application of Amperes Law. We are going to start the lecture with actually Amperes Law, and then we are going to see some amazing geometries. And then we are also going to move on to toroids. So all of this with the application of Amperes Law with me, Shreyas, your physics master teacher at Vedantu. Welcome aboard. Hi Ram, hi Srilata, hi Chaitanya. Hello Sai Telugu, Paparazzo, what a name. Hi Jeevan Icon. Yes, we have started Jeevan Icon. Welcome Vikram, good evening to see all of you. Hi Aarti. Hello everyone PL. This is Shreyas, your physics master teacher at Vedantu, and welcome to the Pathfinder series. So what is this Pathfinder series? It's nothing but a long-term course on YouTube for free for all of you, where we are going to cover all the chapters of 12th standard. Similarly, we have Nurture series for 11th standard kids, and we have the Rank Booster series for the passing out 12th standard kids. And remember, we have already completed in our 12th standard batch in Pathfinder. Already we have completed Gauss's law, electrostatics, current, electricity, and now we are on to magnetism. So we have done quite a bit, and don't worry, we are on track. We are definitely going to complete the portions in the coming few months. So welcome aboard, and nice to see all of you. And do not forget to smash the like button and hit the subscribe button down there, because without your love and support, we won't grow. And thank you guys. Thank you for making us a family of 50,000 lovely warriors who are ready to battle it out in the JEE battlegrounds. Hi Shruti, hi Mahima, hello Ankit, hi Yatin, Shruti. I hope guys you are really motivated. I hope guys you're all pumped up for today's session. By the way, which schedule has been changed, I'm not sure, but in fact I have done something more over here. This is for the 11th standard kids. Well, you 12th standard guys can also attend this. It's free obviously on YouTube. So this is a 5+ hours marathon. I don't know when I'm going to end it. It all depends on your energy and your support, your love. If you shower me more love, probably I might go more than 5 hours. I don't know. It depends all on you. Okay, so that's the backlog covering session on Thursday. So tomorrow for you guys, the 12th standard guys, yep, we have the moving charges, force on moving charges, QV cross B and all of that, and the Lorentz force, so coupled with electric field force and all of that, and a special session on Saturday. That's for everyone. Okay, so in case you missed this class, do not forget to check out our playlist out there. And remember guys, for all the students who are joining in, the pro subscription, all right, we have this amazing deal for all of you. I mean, it's never heard of like any coaching giving you a guarantee and saying that, hey, if your kid does not improve, it's okay, we return back the fees. They don't even return back the fees for, random or genuine reasons. So here we are telling, okay, this is Vedantu improvement promise. You will definitely guaranteedly improve once you are inside Vedantu, and if you do not, well, here are your fees, no questions asked, unless and until you are not attending any classes, of course. And we are confident about this because of our amazing results that we have been producing in the past. I mean, there is a very good chance that if you are enrolled in Vedantu, your chances of getting into IIT, chances of getting into NIT, BITS or any other college is 5 to 6 times higher than other students who are not studying with us. So that's the comparison. I mean, it's crazy, it's extreme, and we have made some amazing changes, and you can check out all the details of our pro subscription plans, which start at as low as 3,060 rupees per month, which is very affordable. And if you want the doubt solving and other things, you get it for 3,870 rupees per month. Of course, you have to use the coupon code SHHPRO, without which you are not going to get that 10% off. Remember that. All right. So let's get going. Thank you, Jeevan Icon, for calling it the best channel plus best teachers. You missed one variable, Jeevan Icon, plus best students. There was one thing missing in the LHS of your equation. Okay. All right. Very good, Vikram. Glad it is very crystal clear, and glad it's snowing in your mind. Hello, Lakshmi. All righty. And half silver play button. Yes, Srilata, it is. Thank you, Paparazzo Shreyas Capri. Oh, I know why you put that name, Paparazzo Shreyas Capri. I gave that title to Shreyas Capri because he's very, very chalu. He's like a spy, special investigative kid or something who gets to know all the inside scoops. He knows where to find amazing pictures, hidden pictures of all the master teachers. So Shreyas Kapri Paparazzo, he's the guy. Okay, so thank you guys, everyone, welcome aboard. So let's get going out there. Yep. Now see, before we start Ampere's law, we need to talk about few terms. So let me just clear it out, because straight away jumping onto Ampere's law is not good. First of all, what is a closed path? Obviously, if you travel and you come back to the same point, like remember back in those olden days in 2019, do you remember in 2019, long time back, you used to start from home, you used to go to the school and while away your time somewhere in some coffee shop or some, I don't know, some snacks, and then you used to come back to home. So that's a closed path. Obviously, you will return back to home. Where will you go? You don't have money, you don't have anything else. You cannot go and randomly sleep on the footpath, right? So you will obviously come back at home. So that's a closed path, guys. And that closed path has a special name. That is called Amperian loop. So what is Amperian loop? It is nothing but a closed path. You come back to the same point. Displacement is 0. Any closed path, I can call it as an Amperian path or Amperian loop. I hope this is crystal clear. All right. So now, having said that, let's talk about current's sign, because this is going to be useful now. The current in the direction of the thumb is assumed to be positive when your fingers curl in the direction of the path. I'll repeat again. The direction of the current is positive. This is right hand thumb rule. When the fingers will curl in the direction in which you travel the path. So let's say, for example, I start from here, go like this and come like that. There might be a current which is piercing through the loop, which passes through the loop. Okay, it's an imaginary loop, it's an imaginary path. It's not a physical path, please understand that. Okay, it's not actual, it's hypothetical. So there's a current passing through it. Then what you get is basically current could be positive or negative. So if you curl your fingers of the right hand, your thumb will point in some direction. All the currents in the direction of the thumb are positive. Any current going opposite to your thumb is negative. Let's take an example to better understand this. You see this yellow colored loop? Well, that's nothing but an Amperian loop. So that yellow colored loop out there, all right, this is nothing but Amperian loop. Okay, it's a closed path. Now you can see certain currents going out, in, etc. Or now you have to decide how you're traveling in that Amperian loop. Let's say I'm traveling like this, I'm going like that. Now what you need to do, use your right hand, curl your fingers, curl your fingers. You see the thumb going this way? That means this current 5 amperes is positive, this current is going opposite to the thumb, so it's negative. This current is in the direction of the thumb, so positive. So that's how you decide which current is positive, which current is negative. Everybody clear about this? Oh, a lot of you showing your right hand, I guess that's your right hand, is it? Oh no, that's your left hand. Oh, but we don't have an emoji like this, so no problems. Okay, everybody clear till this point? How do we determine if current is positive or negative? Exactly, Ankit. This is how you determine. This is what the rule is. So curl your fingers of your right hand according to which you are traveling the path. Now, if some person says, no sir, I'm not going to go like that. Okay, how are you going then? Well, that guy is going like this. That guy goes along the path like this. He starts from a point, goes like that and comes back. So for him, the path will be covered like this. So when he uses the right hand rule, you will see his thumb will be going downwards. So all this current, like 2 amperes is positive, 6 and 5 amperes will be negative. Yes, minus plus minus. Yep, I hope this is clear. Not sure what you mean by that. Windbone, gliding be faster. I'm not sure what you mean. You want me to cover everything taka tak? No, this is a long-term match. Okay, so having said this, shall we go to Ampere's loop law now? Let's check what Ampere's loop law is. Vicky, it's tough to say, man. but you can have combined questions. There are questions where magnetism is combined with mechanics, magnetism is combined with electricity, magnetism combined with EMI. So it's very hard to say, but at least one question. So hardly there are 25 questions in JEE, 25, 30, and there are more chapters. So obviously you will have one question only. So you cannot say, sir, only one question, let's leave it. So every chapter will be like that then. Every chapter will have one question, then you cannot end up leaving all the chapters. Understand that? Okay. So, hi Gian, hello everyone, welcome aboard. Okay. So, here it is. Ampere's loop law. First, when is Ampere's loop law used? It is used to find generally field, magnetic field. It is just like or similar to Gauss law. This is to generally avoid the integration. Yeah, to generally avoid the integration. Now the funny part is the Gauss's law had integration in its formula, and you use Gauss law to avoid integration. So don't get scared, because when I show you the formula, it will have integration. Then you'll be like, sir, you just are telling that we have to avoid integration. But yes, that's the whole point. You can avoid integration, and that's the irony, using Ampere's law. Don't worry about it. Now, what do you need for an Ampere's law? Checklist. You need a loop, obviously a closed one, a closed loop, and you need to know the currents. All right, you need to know the currents, and obviously you need to know the signs of obviously positive or negative. I've just told you which one is positive, which one is negative. That's all. And you need to know which currents are enclosed. You need to know which currents are enclosed currents and which currents are outside. Enclosed currents means all those currents which pierce through the loop. All those currents which pierce through the loop. Any current which does not pierce through the path is an external current. It is not termed as an enclosed current. Keep this in mind. So, first thing, we have a loop. We will have certain currents. Let's say this is current I1. Let's say this is current I2, and so on and so forth. And you might have some another current I3, etc. Now, here is what Ampere's loop law says. All these wires will produce magnetic field around it in a crazy way. Everybody agrees to this? Everybody agrees that all these wires will produce magnetic field everywhere in that 3D space. Now, let's say you start from here. You move a distance dl. What is this dl? A small displacement along the loop. Which loop? Ampere loop. Remember, it's a hypothetical thing. It's not a real thing. At that point, there will be some field. This is that local field. Local means the field at that point. You figure out what is B dot dl. The dot product of field and dl vector. That's displacement. Now you will reach some other point. At that point, there will be a new field, a new displacement. So basically you displace, there is a field at that point, and then when you go here, there is a new field here, and then you displace somewhere else, you move somewhere else, you keep moving. At every point, there is a new magnetic field. So you add them up. Adding means summation. Adding B dot dl, B dot dl, B dot dl, everywhere you add B dot dl, and you reach back to the original point. That's why I put this cyclic integral. So that symbol stands for you are returning back to the same point. So understand, this is called as cyclic integral, because you are returning back to the same point. Since displacement is 0, you are coming back because it's a closed path, remember? And that value of that integral will always come out to be mu naught. Remember, mu naught was the permeability of vacuum or free space into all the total current enclosed. This is the total current enclosed. So this is nothing but Ampere's loop law. I have already given you what is mu naught. Yep. So mu naught was nothing but 4 pi into 10 to the power minus 7 SI units. Now, if you're wondering what is this current enclosed, it's all the currents which are inside. Which currents are inside out of I1, I2 and I3? Come on, answer in the chat box. Come on, answer in the chat box. Which current, yes, is inside, which current is outside out of I1, I2, I3? Oh, join in guys. And even if you're late, please watch the replay. Just rewind the class little bit, 10 minutes or 5 minutes or something, and catch up at 2x speed. I1 and I2 both. Yes, Ampere and loop can be any shape. Remember, Gaussian surface can be any shape. It's your convenience which will make the problem easy. Same way, Ampere loop should be chosen in such a way it makes your job easy. Yep, I1 and I2, correct too. This I3 is external, but out of I1 and I2, who is positive, who is negative, or both are positive or both are negative? Look at that. How are you going? You're going like this. Use your right hand. You also curl your fingers like this. Where is your thumb going? It's going like that. Both these currents are in the same direction as your thumb. So enclosed current in this situation would be I1 and I2 both together. Positive. Yes. No, I2 is also positive. Remember, this direction is also like this. So both are in the same direction. So it will add up. Yep. Both are positive. Excellent. Yes. That's how we need to do this. Now, if there was another current, let's say for example, I4, let's say I4 was here, then now you can see my loop is being traversed this way, thumb is upwards, it is going to be negative. That's what it is. All the principles are very similar to Gauss's law. That's why I told you it's very, very similar to Gauss's law, guys. And you had in Gauss's law, integral of field, electric field with area. Here it is magnetic field with length. And it was enclosed charge by epsilon naught. Here it is enclosed current into permeability. You can compare both of them so that you can remember it easily. You can find some similarities as well as differences. That's how it works. Now remember, this magnetic field is because of everything. Yep, I'm going to cover everything. I cannot see your symbols. There are some weird symbols. Yes, I'm going to cover everything. The person who is wondering and giving some hearts. Yeah. All right. Is there something called as magnetic flux? Yes, Chaitanya. We're going to see magnetic flux also, but that will be an electromagnetic induction, which is the chapter after this. All right. So hold on for that. Okay. So I have put up all the theory for all of you in a beautiful form. So this will be available for you guys to download after a day or something. Usually it takes few hours for us to upload the PDF. It will also come in the description box, as well as you can join all the links which are there in the description box below. Okay, and I hope if you are enjoying the session, do not forget to smash the like button out there. And if you are new to the channel, yes, please go hit the subscribe button. Let's start solving some questions. There we go. B1 vector, B2 vector, B3 vector. What are these? These are magnetic fields. Because of which currents? I1, I2 and I3 respectively. Ampere's loop law is applied. This is the Ampere's loop law. Integral cyclic B dot vector with dl is mu naught I enclosed. Then this B in the Ampere's loop law is which of the following? Think about it. All right. Crystal clear, says Vikram. Nice way of showing that. Oh, his symbols say endgame. Okay, looks like I have not loaded all those symbols or whatever that keyboard is. Can Ampere's loop law be used for solid surface? No, PL. Ampere's loop law is for a path. It's not for a surface. Gauss law is for a surface. Ampere's law is for a path. Path is different from a surface. Understand that. Okay, everybody saying, yep. Everybody saying A, and Margareta Saundari, yes, you can post all your doubts in the comment section. If you have noticed, I take some time, but I do reply to all your comments that you keep posting on our videos. Okay, A, let's have a look. Lot of you are wrong. Oh, who was that guy? B1 minus B2. Guys, understand that convention was for current, not for field. understand at any point, see, that is why these are conceptual questions and you made a mistake. All these currents will create a magnetic field over here, B vector. Now this B vector will be the vector sum of, think about it, this current, okay, this current probably might create some magnetic field like this. Let's say I call B1. Let's say this current probably might cause some magnetic field like this, and maybe that current, all right, might cause some magnetic field like this. So B1, B2, B3 together will produce some net magnetic field. I hope you understand that at any point on that loop, this vector is the sum of magnetic field due to wire 1, magnetic field due to wire 2, and magnetic field due to wire 3. So understand, it is always the net field due to in plus out, all of them, the vector sum of that, all the inside as well as outside. Yes, Margaretha, I just told you. Understood, guys? It was not on currents. You guys got confused. So understand these conceptual questions. See, you should build up these concepts, because then when you solve the questions which I take up later on, you will be not making these kind of silly mistakes. And remember, guys, this is Pathfinder series, and after every chapter, I am going to take up some kind of quizzes which are called mentees, and we are also going to do advanced questions as well. Although I have put up some kind of advanced questions in these lectures, but remember, a proper advanced solving session will happen after every chapter, which I am going to do. Okay, let's go to the next question. Let's see how many of you get this out here. Yes, it's similar to Gauss's law. Yes, correct, Vikram. That's why I said it's very similar to Gauss's law. Which of the currents will be considered in order to find the magnetic field at this point? Which currents will be considered to find the magnetic field, okay, at that point in Ampere's loop law? Think about it. Which ones will you put in Ampere's loop law? Okay, Ampere's loop law in the RHS. Think about it. Which currents will be there? Come on, my warriors. Sabha, PL, Windbone, Sai Telugu, Ramcharan, Nikita, all of you are saying D. Sai Telugu says inside the loop. Okay, come on, my warriors. All the others who are sleeping, come on, wake up. It's a wake up call. Come on, let's see. I1, I2, I3 are inside, I4 is outside. So whenever you write Ampere's loop law, which is B dot dl, is mu naught I enclosed. So in this case, the enclosed currents will be because of I1, of course. It will be because of I2 and I3, but it depends how I am traveling. So let's say I travel the loop like this. This is how you travel, let's say. So if I travel like that, you can see the current is going inside. So I1 will be positive, I3 will also be positive, I2 is coming towards me, so it is going to be negative. So I1, I3 and I2, all the three will be included. So the option would be D. See if you guys got it. Very good. Hello Sarthak, welcome aboard. Hi Shruti, very good. Ankit, I think you made a mistake, no problem. Shruti, very good. PL, I don't know why you changed the answer to C. The correct answer is only D. It's not C. Understand? See, in the option C, there is I4. In the RHS, you only have these currents, enclosed currents. Remember guys, be it Gauss's law, be it Ampere's law, always on the RHS, it's enclosed. But on the LHS, this is always because of inside as well as outside, both of them. That's the difference. Okay, Nitish, how does it matter, man, if we take the classes here or there? Okay, you are here and you can attend it. Both are free channels, man. So attend it over here, okay? And we are also planning some neat kind of sessions in catalysis, okay? Don't worry. So right now you attend over here at least. And by the way, I have created separate playlists over there, so that whenever we take classes, it also automatically gets updated on catalysis, so that any catalysis student is there and he does not have to shuffle around or see where these lectures are. You will see these playlists being beautifully created out there as well. Okay, chalo, let's get going to the next question coming up on your screen. The answer was D, by the way, and here it is. Which of the currents will be considered in order to find the magnetic field at the point P Actually, the question should have been, what is the correct equation? Okay, so what is the correct equation? Which is the correct equation? Don't worry, I'll get it corrected in the PDF. Which is the correct equation, okay, for Ampere's law? Come on, figure this out. This is interesting. You should get this. Yes, I tell you, I did masters, definitely, especially after starting on YouTube. Okay, figure this out. What should be the correct way in which you should consider the currents? Come on, my warriors, figure this out. Only one of them will be correct. Sarthak, don't worry, man. Just focus on the glass. It's okay. Chalo. B. Okay, a lot of you are saying B. Some of you said A. Okay, people are clearly confused. Okay, by the way, if I1 and I3 are both inside, they should have same signs. I2 will have opposite sign. Lastly, I4 is outside. This is outside. So don't consider. Yes, don't consider. Only look at I1, I2, I3. So the ones which have I4, okay, I4 is not there anywhere. Now, I1 and I3 should have the same signs. Can you see I1 and I3 have opposite signs over here? So obviously this is ruled out. I hope you can see this, guys. Similarly, over here, all three of them have the same signs. Same signs over here. All three. This is also then ruled out. Then over here, all of them have same signs. This minus was not there. So again, because of the same sign, you should rule it out. Option C. Here, I1 and I3 have the same sign. I2 has the opposite sign. Hence, this is correct because this and this should have the same sign. This should have opposite sign of that. So only option B is correct. Beautiful. Yes. No, C and D is not same. Be careful. There is a negative sign. Be careful. It's not the same. There is a negative sign. So that makes a difference out there. Okay. Be careful. Alrighty. That's option B. Let's get moving to the next geometry. Now we are going to basically apply Ampere's loop law to find the magnetic field for things like a solenoid or toroid and then sheets. Now, this is a solenoid. Everybody probably would have held an electromagnet or seen it at least in school days, or you would have made some science project where you pass electricity, you take a coil, you wind it over a nail, all right, and it behaves magnetic when you pass current through that coil, and you can attract another nail or another probably piece of nut or bolt using that electromagnet. So this is nothing but electromagnet. What happens is that current will flow through the coil. This current will create this magnetic field. Now if the solenoid is long enough, if it is large and the cross section is small, you will see the field lines inside it are roughly parallel and it is roughly going to be uniform. That's what it is. And you can easily figure out the direction of the field by again using your right hand thumb rule, guys. It's nothing but a coil. Coil placed beside another coil, another coil, another coil. So if the current goes like this, look at that. The current goes like this. Your thumb points in this direction. So that's the direction of the magnetic field. Is the magnet called solenoid? No. The formulas are similar, PL, but it is not exactly a solenoid. It behaves like a solenoid. Now, we are going to see two formulas. A lot of people do not discuss the second formula, by the way. I'll just show that to you as well. The first is a long solenoid. Now, the property of a long solenoid is that, understand the length, alright, the length is much larger compared to the radius. That's how you talk about a long solenoid. The length is much larger as compared to the radius, and you can see inside the solenoid, because the field lines are parallel, what can I say? Come on, guys, write it in the answer. Write it in the chat box. What do you think? The field lines are parallel, so what can you say about the magnetic field? The magnetic field inside is, what is it? It is uniform. Excellent. Length necessarily not infinite, Aditya. If it is infinite, that's the best case scenario. But even if it is like, imagine like 20 centimeter long solenoid and cross section is 1 centimeter, it's okay, fine, no problem. It is like almost uniform. Okay, so field inside is uniform. That's very, very important. And remember, this north and south poles can be easily got using your right hand rule. If the current goes like this, your thumb points this way, so north pole is here, south pole is here. This is like a bar magnet only. If you can visualize it, this is like a bar magnet, almost similar, but it is not a bar magnet. Understand? It behaves like a bar magnet, that's all. Yep. Now, having said that, most of the field lines are inside, and then they have free space after that to travel and come back from the south pole. So these field lines diverge, and because the spacing is very, very large, so the magnetic field outside, what is it? It's almost zero or negligible, and this is a fair assumption. You should remember it, and a lot of concepts can come, or a lot of questions can come on this as well. Magnetic field outside is almost like zero. Samar, this is for 12 students. You can check the description box below. All right. Now I want to know what the hell is the field inside this solenoid. So let's think about Ampere's loop law. So what is my Ampere's loop law? It says cyclic integral B vector dot dl vector is equal to mu naught into I enclosed. Now usually for a solenoid, what is given is this small n. This small n is nothing but total turns per unit length. So this is nothing but turns, okay, the total number of windings, and this is nothing but the length of the solenoid. So this small n is how many turns are there. 100 turns are there per meter, 200 turns are there per centimeter. So whatever it is, number of turns per unit length. Okay, Venkat, if you have joined just now, I think you have missed a lot. So you can do one thing. In YouTube, there is an option for going back even in a live class, and you can catch up at 2x speed. That's something what you can try out. What is a solenoid? Oh my god, I was just telling you all this so long PL. I just showed you that beautiful 3D diagram. I just told you how you made electromagnets in your childhood and your science projects. So basically windings, you know, one after the other in a long way. That's nothing but a solenoid. It's nothing but an electromagnet. Okay, chalo. Now, once you know this property, what we need is a loop, and that is an Amperian loop. Let's see which is my Amperian loop. Okay, let's figure out. I can take anything, but let me choose a convenient Amperian loop, because choosing something else will not make any sense and probably might make this integration very hard. So what we do, let's take an Amperian loop. I feel if I take a path inside, I go outside and come back inside like this. This would be a very good Amperian loop. Check this out. So I go like this, I go like this, I go like this, and I go like this. This is my Amperian path or loop, whatever you can call. Let's say I start from here. This is my starting point. Partially, think of this loop which is partially inside and most of it is outside. Okay, only this part is inside, hardly any part is inside that, most of it is outside. Okay, now here is the thing. Yes, how is the field outside zero, Sabha? Because the field lines diverge. Remember, the strength of any field depends on how closely they are packed. Inside they are all closely packed, but once they go outside, they move out completely till infinity. So they spread. So that's why the field reduces drastically. That's how it is. Okay. Now, this integral, it's a cyclic integral. That means B dot dl for the entire path. How about splitting that complete loop integral into parts, 4 parts? Part 1, part 2, part 3 and part 4. Just split it into 4 parts. It's fine. Okay, let's do that and see what do we get. Integral B dot dl for part 1 plus integral B dot dl, okay, for part 2 plus integral B dot dl for part 3 plus integral B dot dl for part 4. Now on the RHS, be careful, you have mu naught into enclosed current. Whatever current is there inside of it, look at the windings closely, you will see some windings, some wires piercing over here. Can you see that? Can you see? Inside this loop, there are some windings which are piercing through that rectangular loop. Is everybody able to see that? Now, once you get that, all you need to do is basically think about what's the total current inside this loop. So all you need is count the number of loops here. Just count the number of loops. You'll be like, sir, it is 1, 2, 3. Nah, not like that. Assume this length is L. Assume this length is L. So guys, if there are n turns per unit length, how many turns are there in this length? How many turns are there in this much length? If small n is the turns per unit length, the number of turns will be n into L. I hope this is clear. And each turn carries current I, like that. So the total current inside that will be NL into I. That's it. Correcto. So NL is the total turns. Each turn carries I current. So I plus I plus I, NL times. That's the total current. If this much is clear, now let's work out this integral. Trust me, this is very simple. Let's start with this first. Oh, the value of B is 0. Why? You are outside. Remember, the magnetic field outside is 0. So the first part, answer is 0. Okay, so this is 0. Great. For the second part, the answer is also 0. Reason, understand, L vector is like this, magnetic field is like this, the angle between them is 90 and the dot product is 0. That's how dot product works. Dot product of two vectors perpendicular is always 0. So hence this is 0. The reason, because it is perpendicular. Here reason, your outside field is 0. This part, third part, well, this is not 0. B vector is here, L vector is here, so, and it is constant, so it will be just B into the total length. What's the length of this? Well, that's L, of course. And, oh, hold on, plus the fourth part. In the fourth part, B is like that, L is like that. You can see again they are perpendicular, so their dot product has to be 0 because they are perpendicular. Is equal to, obviously, these guys out here, mu naught N L I. And the best part is L and L cancel out, and you are only left with B is equal to mu naught N I, and that's the final answer. That's how you get it. Interesting, isn't it, how to apply Ampere's loop law for such a complicated scenario? But the funny part is, although Ampere's loop law starts with an integration, you don't actually perform any integration. It helps you avoid the complicated maths and gives you the answer within 1, 2, 3 steps. That's it. Jakudi Ratman, why can't you do one thing? Can you just put up all your comments or whatever, your queries in the comment section, or just ping me on Shreyas_Vedantu. I will help you out. Okay, now we are in the flow. I don't want to break that flow up there. Hello everyone. Hello Mila Liz, welcome aboard. Okay, so all the other queries, guys, which are outside the flow of the syllabus right now, just post up your comments. I reply to all the comments. Okay, so remember that, and I have put up the derivation for all of you if you want to read it again. Now, if you do not want to use Ampere's law, then what you need to do is, Chaitanya, you break that loop into coils. Remember field on the axis of a coil? Mu naught I r square by 2 r square plus x square. Now, for each coil, find the field, or due to each coil, find the field, and the value of x will be different. Integrate that. And integrate it from minus infinity to plus infinity because it's a long solenoid, and then you will get the same answer. Why do you want to do that? It will be crazy. Semwal, yes, you can crack, bacha, but I would suggest you to join the proper long-term batches as well, because you need test series, you need assignments, you need the notes, and plus you need a dedicated, what do you say, person to solve your doubts and somebody to always push you. Although we push you over here, but there is something like, you know, a proper system which needs to be followed. You can combine the pro courses with YouTube, but just by YouTube you can crack, no doubt, but then you need to be very, very motivated. You need to be really sincere. You need to be really what do you say, regular and all of that. Even if you miss, then you should watch the replays. Yes, you can still crack using YouTube, definitely. Okay, now the short solenoid formula, this is very important. A lot of people do not know this. If the solenoid is not long, if it is short, then how do you find out the field? Well, it's simple. Look at this formula. For that, join the line from the end to the point where you want to find the field, and join also the other end to the point where exactly you want to find the field. So like this. So this is the other point out there. Okay. So this is the point where I want to find the field. Now drop a perpendicular like this, and now mark this angle as alpha, and then mark this angle as beta. This is alpha and this is beta, that's it. Now the formula is very simple, guys. Magnetic field is mu naught Ni. That was the standard formula for a long solenoid. Now just divide it by 2 and write sine alpha plus sine beta. That's it. That's the answer. That's the formula. Now if you do not believe me, it's okay. I mean, I can show that to you. This works even for a long solenoid. Think about it. If the solenoid is long, so for a long solenoid, can you guess what will alpha and beta both be equal to? Yes, what will alpha and beta both be equal to? Yes, Shruti, we are going to come to toroid also. Hold on. No, this is not for the ends, Chaitanya. This is for any point inside the solenoid, anywhere. Yes, Srikanth, you can take it, but it is not so easy for me to answer. I need to analyze your situation. Just post up your comment or leave me a chat on my Instagram handle. I'll answer that, okay? Both will be 90 degrees. So what will you get? You will get magnetic field as mu naught Ni divided by 2 sine of 90 degrees plus sine of 90 degrees. Sine 90 is 1. 1 plus 1 is 2. 2 and 2 cancel. And you will get mu naught Ni. Oh, that works. That's how you use it. Interesting, isn't it? So this is a generic formula. This is a special formula. Remember, these kind of formulas have also come for straight wires. Yesterday, a straight definite wire. Alright, if you are at this point, the formula was mu naught I by 4 pi r, and then you had sine alpha plus sine beta. Again, the formula looks very similar. So very, very critical formula. Again, the derivations are all there out here in case you want it. Now, going ahead with the questions, and then we are going to go to toroid and then sheets. So let's see how many of you can solve this. The question is, find the ratio of the magnetic field when you are at the center and at the end for a finite solenoid. Remember that. Virat Kohli is in 12th. How many percentage have in this situation to complete JEE preparation? So I'm guessing you are asking how much percentage of the portion you need to complete. At this point of time, 30% almost. Sir, is special theory in JEE? No, Viknesh, it is not. Windbone is saying C, then they said B. Come on, my warriors, figure this out. What is the ratio of the magnetic field when you're at the end and at the center? Jeevan Icon says 2:1. Come on, my warriors. Sai Telugu says B. I don't know. Figure this out. Let's have a look. Okay. So, when you're at the center, I know this. This is simple. This is going to be mu naught Ni. This is, you are at the center. I mean, come on. Both alpha, beta are 90 degrees for a long solenoid. Remember, this is a long solenoid. Okay. Now, when you are at the end, that's when the catch is. So when you are at the end, first join the point where you want to find the field and the end of the solenoid, and the other end of the solenoid and the point where you want to find the field. This angle is almost 90 degrees because remember, it's a very long solenoid, so that will be 90. And the other angle, well, that's 0 degrees. Because the other point is there only. It's a perpendicular. Come on. So this will be mu naught Ni by 2 sine 0 plus sine 90. Sine 0 is 0. Sine 90 is 1. So this will become half. So this will become half mu naught Ni. Now this is half of B center. Now please check what has been asked. Accordingly find out the ratio, because both the answers are there, 2:1 and 1:2. The question says find the ratio on the end to that at the center. So end upon the center. So hence the answer will be 1:2 and not 2:1. I hope this is clear. Yes, option C. Oh, Paparazzo, I think you made a mistake, silly mistake. It was center. No, it was end by center, not center by end. Be careful. Yep. The answer is C, guys. Okay, let's get going to the next question coming up on your screen. Very good. Let's see. There are two solenoid coaxial. That means one inside the other. The axis is same. They are having different turns per unit length and different currents. Now this is multiple choice, advanced type. Let's see how many of you can get this. So guys, the net field inside the inner coil will be 0 in a very special situation. More than one option may be correct. Think about it. Either all are correct, maybe 2 are correct, maybe 3 are correct, or only 1 is correct. So figure this out. If there are two solenoids, one inside the other. So you have a solenoid like this. All right. This is the solenoid inside. And then you have another solenoid like this. So that's the other solenoid. So the question is that here the net field is 0 in the under what condition? More than one options may be correct. Figure this out. You should just know the formula for solving this question. Windbone says option B only. All right. What about others? What do you guys say? Rupa says D only. Remember, this is advanced type. More than one can be correct. I don't know how many options are correct. Sabarish says A, B and C except for D. Interesting. Virat Kohli says D. Shruti says C and D. Sai Telugu says C and D. Capto. Alright. LOL only. L is not there. O is not there. L is also not there, Pallavi. So I think you need to choose between A, B and C and D. Okay. Chala, Chaitanya says A and D. Rupa says C and D again. People are changing the answers now. Interesting. So guys, the only way the field will be 0 if they cancel out. So the magnetic field due to the outer or inner one, which is mu naught Ni, let's say it is in one direction like this, should be magnitude wise equal to mu naught Ni, but due to the outer one. They are going to cancel out each other. That's the whole idea of making the field 0. Mu naught goes, and I'll be left with N1 I1 is equal to N. Just one second. Yeah, you'll be left with N1 I1 is equal to N2 I2. So that's this situation, as well as this situation is also possible. If these two currents are equal, and if these two number of turns per unit length are equal, then also the net field will be 0. So both these situations are correct. A and B is incorrect because if N1 is equal to N2, then I1 has to be equal to I2. They can't be not equal. And same way, if I1 and I2 are equal, then this is N1 must be equal to N2. So hence A and B are wrong. Yep, that's how it is. Very good. Virat Kohli says ABD Villiers. Man, your name is Virat Kohli and you're saying ABD Villiers. Not correct. You're not a very good fan of Virat Kohli. Yo, very good. A lot of people were correct, and that's the answer. That's advanced type. That's why I'm saying these are advanced type questions where you have multiple options correct. So you need to think for every option, guys. You cannot just move ahead. Let's go to toroid. Look at a toroid, guys. I mean, so beautiful, right? So you might be wondering, what the hell is a toroid? PL, I hope you remember what's a solenoid if you're there. So solenoid is nothing but coils wound one after the other, and it's coaxial, or all the coils have the same axis. There is a current passing through it that produces magnetic field. Now, what you need to do, take that solenoid, apply some power, you are Hulk, bend it like Beckham and connect the ends. So what did you just do? Take a solenoid, bend it like Beckham and connect the ends. So the magnetic fields which were escaping out of the solenoid, remember the magnetic fields used to go outside, come back inside for a solenoid. Now when you connect the ends, will they go out? Think about it and let me know. Will they go out? No, right? Obviously. They'll be all inside. They're all trapped inside. The magnetic field lines keep on moving inside. So that's what it is. The red one over here is current. So the current is traveling. So it's like a bent solenoid. And the green lines inside will be the magnetic field. As simple as that. That's how it is. Oh, looks like a fancy bangle, says Vikram. Yep, it is. I mean, imagine some girl wearing this kind of a bangle. It would be crazy. Toroid bangles, we should call it. Toroid bangles. Interesting name. And then probably you can also have solenoids. Oh my god, that would be crazy. Okay, so that's a toroid. That's how it looks. Scary, isn't it? The name looks scary, but it isn't. It's nothing but a solenoid, nothing else. So, what is a toroid? Toroid is nothing but bent solenoid. So guys, think about it. What will be the magnetic field outside the toroid? Figure this out quickly and let me know in the chat box. I'm waiting for your chats. Shruti, you went wrong out there. B inside the toroid? Nah, this is the inside. No, magnetic field is there inside the toroid. Outside the toroid is 0. Yep. Outside the toroid is 0. But the magnetic field inside is same as the magnetic field of a solenoid. Do you guys agree with this? Because this is nothing but a solenoid which has been bent. Yep. Yay, motivational status. Wanna come? You too, bacha. Oh, Monali says, hey, are you wearing a toroid? And the bad thing is that not many non-scientific girls will understand this joke. And probably they might just think you have a bad sense of fashion. Alright, so here it is. The magnetic field of a solenoid is mu naught Ni. So same formula works. And then this N was turns per unit length. Do not forget that, my kids. Now, what is the total turns? Let's say the total windings. You count, you're jobless, you count the number of turns, it's N. What is the total length of this solenoid? Come on guys, let me know in the chat box. R is the average radius of this tube. R is the average radius of the tube. So guys, can you figure out what's the length of the solenoid? If you're not able to visualize, just visualize this. Open up the toroid. It will become a solenoid. What would be the length of the solenoid? Won't it be 2 pi r? And that's the answer. That's what you need to remember. Oh no, it's not a sphere, Jeevan. This is not a sphere. This is a... Oh no, it's not a sphere. I don't know why it looks like a sphere. It's like a tube which is bent. That's it. Oh, it's the circumference, 2 pi r. Beautiful. Excellent. So remember, solenoid and toroid both have the same formulas. You don't have to remember it separately. As long as you remember that, you know, the number of turns per unit length, at length is the circumference of that tube. Okay, chalo, let's start solving some questions based on this. There we go. Here we have the question. Let's see how many of you are really quick at calculations. Calculations are simple. Waiting to hear all your answers. This is a toroid. Inner radius is 10. Outer radius is 12. So you know what to do. Which radius to take. Inner or outer or something else. You figure that out. Total turns 3,500 turns in the toroid. Current, that's also given 11 amperes. And the question is, what's the magnetic field inside the toroid? So that's the question. So meanwhile, I'll just show you the diagram. This is how it's going to look like. This is my toroid. Oops, 1 second. Yeah, so there we go. That's our toroid. These are the windings. And obviously, you will have magnetic field lines coming out of it. Okay, yeah, the magnetic field lines coming out of it. So the question is, what is this magnetic field? And remember, they have given you the inner radius to be 10 centimeters if I'm not wrong, and yep, and the outer radius is 12 centimeter. So figure this out, because the current is also given. The current is 11 amperes. Figure this out. What's the formula? Very good, Windbone. You're going to take that, figure the formula, apply. Sir, please reply on how to get to know that. What should I get to know? So what is fee of Vedantu Improvement Promise? Is the same fee, Prasanna? Yeah. So when you are enrolled, you get the same thing. Yep. Thank you, Saiteja. So in hollow part, it is 0. Yes, Chaitanya, correct. So when you have a toroid, here it is 0, here it is 0, here it is mu naught Ni by 2 pi r. Okay, but this is also considered to be outside only. Think about it. All this is connected only anyways. This is all outside of the toroid. The inside of the toroid means only this much part. Okay, that's what inside of a toroid means. Okay, cool. No, Aditya, it is not. Okay, because you need to be with us for a very long time, no? Then only we can do something very productive about it. All right, so here we go. Let's solve this. Let's apply the formula. B is equal to mu naught Ni divided by 2 pi r. And there we go. What is the formula for mu naught by 2 pi? Achha, I know the value, because remember, mu naught by 4 pi is 10 to the power minus 7. So mu naught by 2 pi, if you don't understand that, no problem. Just put it as 4 pi into 10 to the power minus 7 divided by 2 pi. That's one and the same thing. Okay, multiplied by number of turns, which is 3500, multiplied by the current. What's the current? That's 11 amperes, divided by r. Well, the average radius needs to be taken. So that's 11 into 10 to the power minus 2. So remember, this is average radius. That's what you are going to do always. Now everything is going to get cancelled, like 11 and 11 will get cancelled. 2 pi and 4 pi will get cancelled. That will become 2. And see this, what are you going to get? 35 into 2. Well, that's 70. Okay. And those two zeros are there. That means 10 to the power 2. This 10 to the power minus 7. And this 10 to the power minus 2 comes upstairs. So what are you going to get finally? Check this out. Let's see how many of you have answered meanwhile. 7.7. No. So not 7.7, Rupa. Be careful. Yeah, 0.07. Correct. Many of you got it wrong. Some of you got it correct. Yes. So this is 10 to the power 2, 10 to the power 2, 10 to the power 4, 10 to the power minus 7, and 10 to the power 4 will make it 10 to the power minus 3. So 70 to 10 to the power minus 3 is 0.07 Teslas. Yep, there you go. Please understand, this is 10 to the power minus 7. Be careful. Mitra D, I will wait. Yep, very good, Windbone. You did it. Excellent. So these kind of questions can definitely come in JEE Main's paper. Remember that. And they have been coming in the past few years. So do not think that, oh, this is too much difficult or it's too easy. No, these are very relevant questions for your JEE Main's examination. Now let's go to sheet carrying currents. Now see, if wires are placed close by each other, touching each other, it forms a sheet. Okay, now we all know that if you just have a single wire, let's say which carries current I, it produces magnetic field around it, something like this. This is how the magnetic field looks like around a single wire. We have been doing this last lecture. What if there are two wires placed besides each other? So if you have wire 1 and if you have wire 2 placed besides each other, well, the magnetic field close by will look probably like this. But when you go a little bit far away, it's probably going to look like this. This is how the magnetic field will look like. Very, very hallucinating. So this is how the magnetic field will look like for two wires very close to each other. Now, similarly, if we have multiple wires like this, so say, 2, 3, 4, 5 wires very close to each other, what you're going to see is the magnetic field will look something like this. My God, looks like an insect, and similarly like this. Yep, and like this. So basically, as you expand it, as you have more and more wires, you have those waviness out there, and you will see the magnetic field lines get stretched. Instead of being a circle, it becomes like a stretched circle. You have more wires, it becomes even more stretched. So that's how it looks like. But now if you have closely packed wires besides each other, this wire is besides the next wire, besides the next wire, there is no room for the magnetic field line to complete the circle. So then you will see, and it's very large, look at that, the current is coming towards you. So you are going to see the magnetic field lines going like this. Magnetic field lines going like this. They will come back after infinity, after a very long time. It looks like goggles. Yes, very true. So actually when you see it from the side view, what you're going to see is that at the ends it will curl, and here it will be almost uniform, again curl, and again almost uniform out here. And the same thing is going to look like this. So this is how the magnetic field lines are going to look like. Now because the current is coming towards you, hold your thumb in your direction. Please don't lick your thumb, guys. Yep. And you're going to see the fingers are going to curl this way, and that means the magnetic field will be in this direction. Yep. So the magnetic field will be in this direction. Please remember, the ends are not so relevant because this is at infinity. So there is no point actually speaking drawing the ends. Okay, so there is no point doing that. Now, what's the field? Well, that's simple. Use Ampere's loop law, you will get it. So here is my Ampere's loop law. Oh, by the way, is this magnetic field uniform? Is the B field uniform? Isn't it? The magnetic field is going to be uniform. That's something which I just saw. There is one thing which needs to be given though, and that is lambda. Now this lambda is the current per unit length. Current per unit length, so it is ampere per meter. Keep this in mind. Ampere per unit. Almost uniform, will give it. I mean, we are engineers, we understand, okay, fine, we are not going to deal with those waviness. It's almost uniform, it's okay. Ampere per meter. What does it mean? If you take 1 meter here, what's the amount of current in that 1 meter? That's lambda. Current per meter. If I have many wires closely packed, a lot of current, it has more lambda. Current is less, the current per meter is going to be less. So that's what lambda is, current per unit length. That's the current linear density. Now, when you apply Ampere's law and all of that, you can take a loop, guys, like this. It's not that difficult to see. If you take a loop, let's say starting from here, go like this and come back over there. Assume the length of the loop to be L. You will see when you apply Ampere's loop law, okay, for path 1, this is path 2, 3 and 4, the Ampere's loop law, which is B vector dot dl is equal to mu naught I enclosed. This integral needs to be split into 4 parts, just like we did for solenoid. So integral 1 plus integral 2 plus integral 3 plus integral 4, 1, 2, 3, 4 will be equal to mu naught into enclosed current. Think what is the value of enclosed current? The value of the enclosed current. How much current is piercing through it? Oh, I know this. Current per unit length is lambda. The length is L. Lambda amperes is there per meter. So for L meters, there will be lambda L amperes of current. So hence enclosed current is lambda L. Yes, it is lambda L. Now think about the integrals 1 and 3. The integrals 1 and 3 both will be 0. Reason? Oh, look at that. It's perpendicular to the field. L vector and B vector are perpendicular. So cos or the dot product will be 0. That's because it's perpendicular. But integral 2 and 4, oh, that is B into L. B into L. So it's going to come 2 times BL, and obviously BL is also going to come over here. See if you guys understood this concept. For second and fourth part, this part, B vector and L vector in the same direction. So B dot dl will be, obviously the angle is 0, so cos 0 is 1. So B dl cos 0, and the total length is L, that's why BL. So this will be 2BL, by the way, is equal to mu naught lambda L. So B will be mu naught lambda divided by 2. That's the answer. Mu naught lambda by 2. Very important result, you should remember it. Alright. Soumyadeep, it would be for sure Einstein and Newton both. And actually, I would incline also more towards Tesla. Nikola Tesla. Okay, so that's the answer. Beautiful result, you should remember it. Okay, now let's do some questions based on that. By the way, the proof has been also put out here. How lambda L sub R, remember, okay, let me just go to the previous slide. Because lambda is current per unit length, so in that length L, how much current will be there? Current per unit length into the length will be the enclosed current of that Amperian loop. I hope that is clear, Sama. No? Okay, great. So let's do a question, and hardly few things are remaining now. Let's do this. Tapat. Okay, Paparazzo has noted it. Very good. A lot of thumbs up coming up and fire as well. Two sheets are carrying currents, and the question is, what's the magnetic field in all the regions? Let's do this. Where is the current flowing? Plus Y and minus Y. Oh, by the way, this is x-axis, this is my y-axis, and this is my z-axis. Now, okay, this is x. The current is moving in y-axis, that means here, okay, it's going like that. So that current density is lambda, and the current is also coming like this. And how much is the density? That's 4 lambda. Okay, that's also given to me. Now, before going ahead, in fact, what I will do is figure out what is the field due to each one of them. Yes, what is the field due to each one of them? Now first let's start with this lambda guy. Current is going up. Use your right hand, point your thumb in the direction of the current, see how the magnetic field lines are curling. If you are on this side, the field is coming towards you. Look at that. If you are on the left side, the field is towards you. That means I should put a dot. But if you are on the right side, anywhere, because of this current, the field lines are going inside. So I'll put a cross over here. And the formula for the magnetic field, because of that, will be mu naught lambda by 2. Great. Similarly, because of this 4 lambda, the current in that sheet going like this, put your thumb downwards, hold your hand like this, put your hand downwards. You can see the fingers curl this way. That means if you are on your right side of this sheet, the field will come towards you. Yep, the field will come towards you. But if you are on this side or left side of this sheet, obviously the field lines are going inside, you can see that. So it's a cross or a cross over here, anywhere on the left side of this sheet. PL, just use it properly, man. Just learn to twist your hand. You need to learn that. Please do not use that stupid Fleming's left hand rule, Fleming's right foot rule and all of that. Don't remember that. You just need to twist your hands. It takes some time and some practice. You need to orient your thumb in any possible direction and see what happens. That's all. So for this guy, you can see the current is going up. So fingers are curling like this. So if you're on the right side, the magnetic field is inside. But if you're on this side, then it is towards you. Similarly for this guy, point your thumb down like this. If you're on this side, it is coming outside the board. But if you're on this side, then you can see the field lines are going inside the plane of the board. Yep, that's it. So now that field will be mu naught into 4 lambda by 2, which is mu naught 2 lambda. So let's say I call this B2 and let's say I call this B1. So that means now I know what will be the field here, here and here. Like in this region, I can see both of them will be adding. So B1 and B2 will add. So it will be mu naught lambda and you have half plus this 2. So it will be nothing but 2 plus, that will be 4 plus 1, 5. So 5 by 2 mu naught lambda in this direction. It's clearly seen. Half plus 2. In this scenario, one is coming outside, one is going inside. The one going inside is more powerful. So it will be mu naught lambda 2 minus half, and that is going to give you 3 by 2 mu naught lambda. The one which was going inside, the red one was more powerful, so it is inside. And here also it will subtract again, but this case mu naught lambda by 2 into 3. This case it will be towards us because the red one is more powerful, remember that. Okay, that's how it works. Yeah, I don't know why people use left hand rule. Flemings, they mark this ILB, BLV, QVB, and this right, it's very confusing. That's why always I don't like to confuse my students. And you remember, in the examination hall things will look even more confusing. So always stick to the cross product right hand thumb rule. Nothing else you need apart from this, remember that. Okay, cool guys. So that was that. Now let's see how many of you can answer this question. This is a beautiful question that I want to solve before we end the class. Let's solve this question. A beautiful question for all of you. A solid cylindrical conductor has a radius r and uniform current density, and then the question is, find the magnetic field inside that wire at any distance r. Let's not worry about the options. Oops, something has gone wrong. I think the slides order have changed. Acha. Okay, first let's solve this question and then let's go to that question. Okay, this will be easier. This will be easier. Okay, so don't worry about that. I'll come to that question. So there is a current which is coming towards you, and there is current going inside. There's an empty space here and outside. Coaxial cables. The inner wire, the current is coming towards you. The outer wire, the current is going inside. So guys, what do you think will be the magnetic field in region 1 and in region 2? Just plain simple application of Ampere's loop law. No, not homework. PL, it's not homework. Okay, think about it. For region 1, I'm going to do this right now because we are a little bit short of time. For region 1, who is the enclosed current? For region 1, who is the enclosed current? Isn't this the enclosed current? So when you actually use B dot dl is equal to mu naught enclosed current, you will have I1. So that's why B will be there. I mean, it will not be 0. B1 will not be 0, I1 will be there. But when you take this loop, the second region, as the Ampere's loop law, and you write B dot dl, you will have mu naught I1 minus I2, because their directions are opposite. The total enclosed current is both the currents, but the good part is they are equal currents. So this I1 minus I2 will be 0, hence B will also be 0. So only correct option is option A. No, a lot of you are saying B or D or B or C. No, this is the correct option. Look at that, the equal word plays an important role. If they were not equal, then both will be non-zero. Understand that, option A. Alrighty, let's get going to the next question. Okay, yeah, that's the answer. Okay, now coming back to that question which I was just telling you about. Okay, there is a solid cylinder and you have radius r. Inside that solid cylinder you want to find what's the magnetic field. This is an important question, and whatever answer comes out, you have to memorize it because there can be a direct question on this formula. So clearly observe this. We are going to quickly do this. Very, very important. This is a long wire. Okay, carrying current. Inside that solid part, what is the magnetic field? Outside the wire, we know mu naught I by 2 pi r. Inside the wire, what is the field? So first, take an Amperean loop. How? Draw a circle. Just draw a circle. Okay. Now that's my Amperean loop of radius r. So I'll just mark it very clearly so that everybody knows what we are doing. So this is my Amperean loop. Okay. Now, what do you think is the enclosed current? I enclosed. Well, that's simple. Inside this Amperean loop law, the current enclosed will be the current density multiplied by the area of that loop. Remember that current I which is passing through the entire gray part. some part will be passing from here, only some of the current will be passing from inside. So that's why the best thing to do is the current passing through this area is density multiplied by area, current density multiplied by area. So what is the current density in general? Well, if this radius is r, the current density will be nothing but total current divided by total area. Total current divided by total area, that's why pi capital R square. I hope this is clear. Multiplied by this area is the area inside the shaded part. What is the area? Because I want the current which is passing in that shaded area. So that will be pi small r square. Hence that enclosed current will be pi r square by capital R square. This is what is very important. No, Vivian, it is not 2r by 3. Be careful. It is I r square by r square. This is the most crucial part of this problem. Finding the enclosed current, and all we did was assumed, or rather it's given that it has uniform current density. It is clearly mentioned. Current flowing per unit area is same. So if current I was flowing in pi r square, how much current is flowing in this small pi r square? Unitary method. Thank you, Athira. Now let's use our Ampere's loop law, which is B dot dl is equal to mu naught I enclosed. Okay, I enclosed, I already know, I just figured it out. I r square divided by r square. How about this? I need to show what is dl and what is B. Well, I'm traveling this loop, so I travel dl distance. At that dl, the magnetic field is B. I travel dl, magnetic field is B. I travel dl, magnetic field is B. I travel dl, magnetic field is B. So everywhere I go, I have some magnetic field, and because I'm at the same distance from the center, value of B is same. Value of B is same because I'm at the same distance from the axis. That means I can take this guy outside, number one. Number two, the value of this dot product will come out to be 1 because cos of 0 degrees is 1. And why is this 0? Reason, B vector is always parallel to dl vector. That's the reason for that. Very, very crucial step out here. The dot product of B vector and dl vector is 0 because it's uniform in there. Alright, it's constant throughout magnitude wise, and you take out that B vector outside. So the moment I take out that B vector outside, I am only left with integral, dl, that's it, no vectors now because I have already taken care of the dot product. Now, exactly Chaitanya ji, that's the step before that 2 pi r. Now think, what is the integral of dl vector, or dl actually, dl plus dl plus dl plus dl. What will you get? You will get the length of that purple, that bluish line. What is the length? It's nothing but 2 pi small r, not capital R. Understand? You're traveling this path, you're not traveling the outermost periphery. Oh, okay. And this is nothing but mu naught I r square divided by r square. Now you can cancel out, like this r and this r will go, nothing else will go. Now bring this 2 pi downstairs and you will be left with B is equal to mu naught I r divided by 2 pi r square, and this is something which you should remember because this is a field inside of a long wire, where r is less than r. Okay, r is less than r, you're inside that wire. If you're outside, you already know the formula. It was mu naught I by 2 pi r. That was something which we already know. Very, very important answer. Interesting question. So guys, that's the answer, option C. Now homework. This is your first homework. Okay, you can take a screenshot of this. The second homework is this one. Post all your comments below after the video ends. And this is your third homework question for tonight. Please post the answers as soon as possible. Don't try to look at the solutions or the answer key before posting the comments. And if you still do not get it, remember all the answers will be posted on our PDF, and you can see the PDF after some time or after a few hours, which will be posted again in the description box below. Now, very important thing is you will find a lot of links out here in our description box. So if you go to our description box out there, and what you will get is, yep, all the important links for checking out all the different courses. Like the crash course, there is a link, there is a pro subscription link, and when you click on this pro subscription link, you will see all the details of the pro courses out here, like the entire syllabus which will be taught, okay, everything, physics, chemistry, maths, and all the amazing teachers. You can see Wazim sir out here, Mohit sir for physics, Amit Kumar sir for maths, and the timings, obviously both batches are available, English and Hinglish mixed, the entire syllabus, the timetables, everything, and all your frequently asked questions are out here. So check this out, because I feel that you should go for either the light or the classic or the plus version. And remember, these are the final costs. All right, after you use the discount coupon code, which is SHHPRO, you save 10%. And in the classic version, apart from getting everything like assignments, tests, modules, you also get the doubt solving. The only difference is that if you want the plus version, then you also get the personal mentorship. So you can see everything has been mentioned. And remember, you don't have to pay this amount upfront. You can pay easy EMIs like 3,800 rupees per month, or you can even try it out for 1 month. So my advice is start enrolling in these batches and start studying with us, with YouTube as well as the pro subscription. That will be a very good combination out there. So you can see all the details have been mentioned, what and all you are going to get in each kind of package. And the packages are very, very cheap, and you can use this coupon code out there. Chalo guys, that's it from me tonight. Good night. Very good, Ankit, you made notes. Nice to know, Vikram, you understood everything. Very good, PL. Bye-bye, Chaitanya, Sai Telugu, Windbone, Papra, Zor, Shruti. Can B change speed? No, Shruti. In fact, we are going to talk about it tomorrow. Next class tomorrow at 7:30, force due to magnetic field on a moving charge. That's what is going to be there tomorrow at 7:30, so do not miss that class. Hasta la vista. This was Shreyas here, your physics master teacher.